Today we are discussing about temperature compensation for constant current bias. We know that in the last class, with the help of the constant current bias method, we are determining the emitter current IE3 equal to VEE minus VEE into R2 whole by R1 plus R2 minus VBE whole by RE. Okay, so this is where consider the equation number 1. With respect to the above equation, we are conclude the one important point is in this equation VEE constant and emitter resistance RE constant and these resistors R1 and R2 also constant. Okay, but in this above equation, the VBE is not constant. It means that the VBE voltage is dependent on the temperature. Okay, so here we know that for 1 degree centigrade temperature, 2.5 millivolts VBE value changes. Okay, so here the VBE voltage can be changes with respect to temperature. Okay, and in this above equation the VBE value changes, then the emitter current IE3 changes. Okay, and we know that the operating point of the differential amplifier is the function of the IE comma VCE. So here the IE value changes, then the operating point or the Q point of the differential amplifier changes. So if the operating point changes, then this differential amplifier is not giving the proper output. Okay, so to overcome this problem, we are improve the thermal stability of the this constant current bias circuit. Okay, and here we are using these two resistors R1 and R2. So in this constant current bias circuit, we are replacing the resistor R1 by the two diodes D1 and D2. So with help of these two diodes, we are giving them temperature compensation. Okay, and now here we are drawing the constant current bias circuit. Okay, so here we are drawing that circuit, and we know that circuit having the dual input balanced output difference amplifier. Okay, so here we are connecting the RS, and this is we are concerned the V2 voltage, and here we are connecting the RS, and here we are connecting the input voltage, and this is the RC, and here we are concerned the output. Okay, based on these two inputs and connecting the output, this is we are called as dual input balanced output, and here we are connecting the constant current source. Okay, but here we are connecting the resistance R2. Okay, in the last class at the constant current bias circuit method, here we are connecting the resistor R1. Okay, so we can replace this resistor R1 by the two diodes. Okay, so these two diodes provide the thermal stability. Okay, and we are maintaining the emitter current is constant. Okay, this is we can consider the diode D1, D2, and voltage drop across the diode D1 is VD, and the voltage drop across the diode D2 also VD. Okay, as per our convenient point of view, we indicate the polarities of the diode. Okay, plus minus. Clear? And this is the base terminal of the Q3 transistor, and here current is IC3, and in this branch current is IE3. Okay, and here we are connecting the emitter resistance RG. Okay, and here we want to determining the how this circuit can improve the thermal stability. Okay, with respect to Q2 transistor, we are mentioned this base voltage is VB3, okay, and this emitter terminal voltage is VE3. Clear? The voltage between the base and emitter is VBE. Clear? And here we want to estimating the emitter current IE3. Clear? Now here emitter current IE3 equal to this voltage minus this voltage by this resistor, that is VE3 minus VEE whole by resistance RE, that is equal to VE3 or VE plus VEE whole by emitter resistance RE. This is where consider the equation number 1. And now we want to estimating the this emitter voltage V3. Okay, and we know that the voltage between the base and emitter is VB. Okay, and this terminal voltage is VB. As per our convenient point of view, here we are redraw the this circuit, that is this is the base voltage VB3 and this is we are consider the VBE. Okay, and this end we have the voltage is VE3. As per our convenient point of view, indicate the polarities of this voltage, that is plus minus and plus minus. Now we can apply the KVL in this loop, then we will get minus VB3 plus VBE plus VE3 equal to 0. Therefore, the emitter terminal voltage VE3 equal to what? VB3 minus VBE. This is we are consider the equation number 2. Okay, and now we are determining the this base voltage VB3. Clear? And with respect to these two diodes, okay, the overall voltage drop across this branch is 2VD. Okay, and this end we have the base voltage and this end we have the voltage VE. Okay, as per our convenient point of view, here we are mentioning the voltage is VB3. Okay, and this voltage we are consider the 2 into VD. Okay, why I am writing the 2 into VD? Because each diode offer the voltage is VD. Okay, so the diode D1 voltage drop is VD and the diode D2 voltage drop is VD. The overall voltage drop across this branch is 2VD. Okay, so here we are mentioning the voltage 2 into VD, and other end we have the minus VEE. Okay, so here we are mentioning the polarities of this voltage, that is plus minus and plus minus. This is the minus and we have the plus. Okay, now we can apply the KVL in this loop, then we will get minus VB3 plus 2 into VD minus VEE equal to 0. Okay, therefore the VB3 voltage is equal to what? That is 2 into VD minus VE. This is we are consider the equation number 3. Now this equation number 3 we are substituting the equation number 2. Therefore VE3 equal to VB3. What is the VB3? That is 2 into VD minus VE minus VBE. This is we are consider the equation number 4. Now substitute the equation number 4 in equation number 1. Therefore, the emitter terminal current IE3 equal to VE3. What is the VE3? That is 2 into VD minus VEE minus VBE plus VEE whole by this resistance RE. Okay, so here plus VE and minus VE cancel. Therefore, this emitter terminal current IE3 equal to 2 into VD minus VBE whole by RE. Okay, so in this circuit, if you are using the both the diode and BJT characteristics are same, it means that the voltage of the diode VD same as VBE. At that time we will get the IE3 equal to 2 into VD minus this VBE we are considered as VD whole by RE. Therefore IE3 equal to Vd by Ra. It means that this emitter terminal current is dependent on the diode voltage. Okay, but here our doubt is how this circuit can improve the thermal stability. Okay, it means that in this circuit, if the temperature is increases, okay, at that time this collector current IC3 increases. Okay, if the collector current IC3 increases, at that time this overall current I also increases. The current I increases, then this ID current increases. If the ID current is increases, the base current of this Q2 transistor is decreases. The base current decreases, then this IC3 is decreases. It means that with respect to temperature, how much amount of current is increased at this collector terminal, the same amount of this diode current also increases, then the same amount of this current is decreases, then overall current also decreases. So in this way we are maintaining this emitter current I is constant. Okay, thank you.